Is it audible clearly? Yeah, great. So, do you have any questions from yesterday's class? Got it? Okay. So, we just discussed, that is only the scalar fields and the vector fields, right? So, from there actually, suppose if you take a vector field function, so vector calculus. So, let us consider a vector field function. So, in the vector field function, right? So, let us say if it is f is equal to some function of x comma y comma z into I, some function of x comma y comma z, xi of x comma y comma z, k, right? So, this is a vector field function. Now, to find out the derivative of this particular function, let us say x is a function of t and y is a function of t and z is a function of t. So, here actually this is another way of representing the same thing. Let us say if it is a function of t, or it may be a parametric form where t is the parameter. Now, if you want to find out the df by dt, which is nothing but the derivative of the vector function. So, if you want to find out the derivative of the vector function, now f is indirectly a function of time in total, right? So, here this is limit delta t tending to 0, f of t plus delta t minus f of t divided by delta t. So, this is what is defined as the derivative of the function with respect to time, right? So, the fundamental principles of calculus will not make any difference here. So, if the variable is selected, that variable with respect to t, if you want to do the derivative, then it's going to be, this is limit f of t plus delta t minus f of t, where f is a vector, f of t plus delta t, vector field function and its direction at a time of t plus delta t, right? And then this is what is defined as the df by dt. That means you can apply the fundamental calculus principles even on the vector fields as well without having any difference. Got it? Only thing is you have to be separating into 3 different directions. Now every direction is treated separately. That's the only difference you can make out from this. Got it? So here, if you multiply a vector with a scalar function, now actually usually whatever we discussed as part of +2 standard is only the constant functions or the constant values of vectors. But here what we are going to deal with is the variable functions, that is the functions with multiple variables. That is, suppose if I have a vector g, capital G. So this is a vector. Now this vector is a function of x comma y comma z. And let us say this f is a scalar field. So this scalar is again a function of x comma y comma z. Now this is a vector field and this is a scalar field. Now these two are actually multiplied together. I call this as f. So this f function is nothing but f into g, where g is a vector and f is a scalar. So if you want to find out the derivative of this, which is nothing but the fundamental UV principle of the vector, so UV principle of the calculus, you can apply on this. So if there are 2 different functions u comma v, if you wanted to do the derivative of this, then this is, so u into dv by dt plus v into du by dt. So this is the derivative. Now here, when we are dealing with the vectors, be cautious that the order is not changed. But in this particular case, it's okay. But when cross product comes into picture, the order needs to be followed there. So here, you can apply df by dt exactly in the similar manner of the same principle, whatever we used as part of uv. So here, f into dz by dt plus df by dt into g. So this is how actually you can apply the derivative on this particular function as if like it is a normal UV principle, though there is a scalar and there is a vector present here. Exactly in the similar manner, if you wanted to find out the product of 2 different vectors, which is nothing but the, let's say this is the h vector, So H is the scalar given by, so F bar dot G bar, where it is a dot product. So this dot product will result into a scalar value. So this scalar is a function, not a constant. This is also a vector function. This is a vector function. These two together, dot product will make a scalar function. It is nothing but x comma y comma z. So here dh by dt, if you want to find out, this is f dot dg by dt plus df by dot g. So this is how you will be finding out the derivative of the function if there is a scalar product between two different vector fields. Exactly in the similar manner, even if you have a cross product, then also you will be following the same principle. That is, let us say H is defined as F cross G, then dH by dt is given as F cross dG by dt plus dF by dt cross G. Now here actually the order makes difference here. So you should not be interchanging this. Got it? So dG by dt and then F cross. So you should not put this one here and this one here. So if the order is changed, then the sign is going to be changed. That's why when we are dealing with the product of the vectors, you try to maintain the confusion so that you don't get any confusion in this. So this is how actually scalar function that is getting multiplied. Then you can apply the UV formula this way. Scalar product between two different vectors. This is how you can apply. And if there is a vector product, then the same thing you can apply even here as well. Got it? Note down this. Yeah, scalar triple product and vector triple product also exactly follows the similar principle. Yeah, we'll do that. Note it down. Done? Okay. So the scalar triple product of three different vectors is nothing but, suppose if I have f, g, h or three different vectors like this, and then if there is a square bracket like this, then we call this as the scalar triple product. We mean here actually the scalar triple product always results into a scalar. Into a scalar is here, this is f cross g dot h. So this is what is the scalar triple product. Now here f cross g you need to do first, then you can come back for the h. Now the order doesn't make any difference. You can take any order. That is, even if you take f cross h dot g, it will not make any difference. So here this needs to be done first, then it is the next. Why? Because if you take this one first, that is g dot h will result into a scalar. Now with a scalar you cannot do a cross product. So cross product has to be done only between two different vectors. But a dot product will result into a scalar. So that's why you have to do the cross product first, so that you will get a resultant vector. For that resultant vector, you will be doing the dot product with the h. Then the result is going to be a scalar value. Now, even if you change the any order, that is h cross f dot g will also, even this also results into the same value. So all these things, if these three are representing three different sides of a parallelogram, then this scalar triple product will result into the volume of that parallelogram. So that's why that volume number will be a scalar. So this is the fundamental principle behind this. Got it or not? So this way, if there is a scalar triple product, then for that, if you wanted to apply the derivative for it, then it is going to be d by dt of fgh. So this is going to be, so df by dt gh scalar triple product plus by dt h scalar triple product f g dh by dt scalar triple product. So this is how actually you have to apply the principle of UVW, wherein d by dt of UVW is equal to du by dt into VW plus d by u into dv by dt into w plus uv into dw by dt. So this is the product rule in case of three different functions that are involved for the product principle of calculus differentiation. Now here, exactly the same thing we are doing it here. So this is the scalar triple product. For that you will be applied. So the scalar triple product for df by dt and gh, and scalar triple product for f and dg by dt and h, and scalar triple product for fg and df by dh by dt. Right? So this is how you will be applying. Now exactly in the similar manner, if there is f cross g cross h, so this is the vector triple product where all the three are the vectors and the result is also a vector. Now here also this result actually exactly it follows the same principle of the UVW. Now here any order you can take it, that is f cross g cross dh by dt. So this is d by dt of f cross g cross h. So this is plus f cross dg by dt cross h plus df by dt cross g cross h. So this is how you will be doing the vector triple product derivative. Got it? Understood? Okay. Note it down. So if you change the order, exactly you have to follow the same manner. Got it? So if you change this to here and this to here, it will make difference a sign, because A cross B is not equal to minus of B cross A. So this is how actually it will get impacted if you change the order. Got it? Done? Noted? Okay. Now a vector whose magnitude is constant, then the derivative and the original vector are always perpendicular to each other. Now let us prove how it is going to be. Prove that a vector whose magnitude is constant will be perpendicular to its derivative. So can you try to prove that? Can you try to prove that? Based on the knowledge whatever I have provided just now. So try to prove that. See this, a vector whose magnitude is constant. Now actually, if I take the vector f, let us say this is a function of t. So this is a vector function of t. Now, if I take the dot product with the same, then this is going to be mod f of t whole square, right? So this magnitude actually, he said it is c. It's a constant. So then f dot f is equal to constant. If you take the derivative on either sides, then this is going to be d by dt of f dot f is equal to d by dt of the constant. Now this is f dot df by dt plus df by dt dot f. This is equal to 0. Now in case of scalar product, if the order is interchanged, the magnitude is not going to be impacted. So hence f dot df by dt is equal to df by dt dot f. So both are one and the same. So even if you change the order, it won't make any difference in case of scalar, because a dot b is equal to b dot a, unlike scalar product, vector product. So from this principle, you can interchange this. Hence this can be written as 2 times of f dot df by dt is equal to 0. Now both are vectors. This is a original vector and this is a derivative vector. 2 different vectors are there. Now 2 different vectors whose dot product is equal to 0. Now the conclusion from this is both are perpendicular to each other. Then only the dot product will result into a 0 magnitude, right? So as the dot product results into 0, and this happens only when both the vectors are perpendicular to each other. Hence f and df by dt are perpendicular. Got it? Note down this. Done? Okay. Now, exactly in the similar manner, can you do a different phenomena wherein prove that a vector whose direction is constant instead of magnitude, now it is direction. Whose direction is constant will be parallel to its derivative, not the perpendicular. Parallel to its derivative. Can you prove this? Yeah, cross product, obviously. So direction if it is constant, then cross product should come out to be 0. Okay, so let me solve this. See this. So let us say there is a vector f and this vector is a function of t. Now this vector can be expressed as its magnitude f of t getting multiplied with a unit vector which is nothing but g vector. So where g is a unit vector, g cap is a unit vector in the direction of f. So you can express this vector f as f of t into g cap. So where g cap is a unit vector in the direction of f. So you can express this way, right? Any vector can be expressed as a unit vector getting multiplied by its magnitude, right? So based on this understanding, so what you can do is, so df by dt you can calculate, and then you can find out 0. Then you can conclude that they are parallel to each other. Now based on this understanding, try to find out df by dt value and tell me how much you got it. Okay, so this one, see this, so df by dt is nothing but f into dg by dt plus df by dt into g, right? So this is df by dt value. Yeah. Now here, if you apply a cross product on this, then this is f into g cross f into g cross of f into dg by dt plus df by dt times of g. Now here, this is the derivative part, this is the original f part. Now here, f and f, this is a scalar multiplication, f square, and then g cross dg by dt, and then plus here f into df by dt, g cross g. Got it? Now this is dg by dt is equal to 0, since it's a constant direction, constant vector. So if it is a constant vector, then dg by dt is coming out to be 0, because the derivative of the constant will come out to be 0. And then g cross g is equal to 0, because the parallel vectors cross product is always equal to 0. So this part is 0 and this part is 0, hence this right side part is going to be 0. Got it? So since g cross g is equal to 0. So once you get into this, then this is f cross df by dt is equal to 0. Hence, these two are parallel vectors. Got it? Hence, f and df by dt are parallel. But you can note down this. Yeah. So curl for constant direction. Yeah, I think so. It should come out to be 0. Yeah. Got it? Because it is having the same direction, right? So if it is having a constant direction, it has to come out to be 0, because there is no curl part of it. Noted down? So these are some of the calculus operations on the vector fields. So note down one more. If A is equal to phi t square into I, if A is equal to phi square into I plus Tj minus T cube K plus Tj minus T cube K, B equal to sin Ti minus cos Tj, sin Ti minus cos Tj. Find d by dt of A dot B and d by dt of A cross B. Can you find out this? . So you can straight away do a dot product and then apply the derivative of it. So that is one method. Or else actually you can apply the principle of A dot dB by dt plus dA by dt dot B. So this is one method. Actually do a dot product and then apply it. Exactly in the similar manner you can do this one as well. Got it? So there is nothing new here. You just need to do simplification. Nothing more than this. Got it? So here A cross so this is how you should be doing it. So you can note down the answer, you can simplify on your own. So the first one, this answer is 5t square cos t, 5t square cos t (11t sin t minus cos t) plus 11t sin t minus cos t. So this is the first one, and the second one is, it will be a vector t cube sin t minus 3t square cos t times I minus t square times t cos t plus 3 sin t. J five t square minus 1 sin t minus 11t cos t. This is K. So this is the vector product. Got it? So you can cross check it. So methodology is simple. Only you need to do the simplification part of it. Got it? So these are the answers you can note down and verify. Done? I hope you are aware of the fact that if you want to do the cross product, so let us say A is equal to x1 into I plus y1 into j plus z1 into k, and then B is equal to x2 into I plus y2 into j plus z2 into k. If this is the vector, then A cross B you can find out as I, j, k, x1, y1, z1, x2, y2, z2. For this, you need to find out the determinant. This is the methodology of finding out the cross product of two different vectors. So the same principle you have to be applying it here. So it takes a lot of time in simplifying this. Got it? Any questions? Okay. Now coming to the gradient. So for the gradient actually, so there is an operator called del. So del is defined as del is equal to I dou by dou x plus j dou by dou y plus k by dou z. The del operator. Now applying on a scalar value, applying del on a scalar value or scalar function, it results into a vector. That vector is given by del phi. So del phi is nothing but I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. And this is termed as, so del phi is called as gradient. So this gradient is not a new term. This term is nothing but slope. In our mathematics, we call this as the slope. Now, the same slope value is calculated in three different directions, I, j, k directions, and then put it into a vector format. So, the functional change in the direction of x, the functional change in the direction of y, the functional change in the direction of z. So, this derivatives actually put it into the vector form. This is what is defined as a three-dimensional slope or gradient. Got it? So, this gradient will results into a vector which is normal to the surface of phi of x, y, z is equal to constant. Let is equal to constant. So, this is what we call as a level surface. A level surface, we mean the magnitude of this function value on this point, any point on this particular line or on this particular surface is always constant, is called as a level surface. Now, on this level surface, if there is a change in the value of level surface to a different value, that is, let us say this is phi plus del phi, phi plus phi, that is a function value. Now, if there is a change in the value of del phi, so this del phi value is represented with this particular one. Now, that is with respect to the positional vector r is equal xi plus yj plus zk. This is the position vector of any particular point on that particular surface. Now, if there is a change in the position of that particle, then this is dr is given as dy into j plus dz into k. Now, let us find out the relation between the change in the function value and the change in the point of a point on that particular function. Now, for that, let us take the dot product of del phi and del r. So, this del phi is a vector and dr is a vector. So, this product is I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z, and dot product with dx into I plus dy. So, this is with the dot product. Now, this is dou phi by dou x into dx plus dou phi by dou y into dy plus dou phi by dou z into dz. Now, if you carefully look at this, this is nothing but the functional derivative d phi. Got it or not? Is this understood or not? So, the dot product of the del phi and dr. So, dr is nothing but the change in the value of position. Suppose if this is changed to a different value, this one. This is what is dr. And then del phi is a vector. Now, actually, I am trying to find out this vector. What is the direction of that particular vector? For that, I have taken a dot product between these two, but this results into this one. Now, this result, suppose, let if del phi is tending to 0, which essentially means that del phi is nothing but the functional surface change. So, this is phi is equal to constant, and this is phi is equal to constant again, but with a different constant. This is C1. So, here also phi is constant, and here also phi is constant, but a different constant. So, this is one level surface, this is another level surface. Now, if there is a change in the value of r, that is dr, then there will be a change in the function value d phi. Now, that's what is termed as the derivative of the function phi of x comma y comma z. D phi can be written as dou phi by dou x into dx, dou phi by dou y into dy, dou phi by dou z into dz. So, this is nothing but d phi. So, this d phi value, if it is tending to 0, we mean, suppose if you take very next level of surface or exactly a point on this, suppose if I take a point on the surface itself, then d phi is going to be 0, correct or not? If d phi is equal to 0, then dr tending to 0. Now, if that is the case, the product, this d phi value will come out to be 0, right? So this d phi value is coming out to be 0. Then this is d phi is nothing but del phi dot dr. Del phi dot dr is equal to d phi is equal to 0 as on the same surface. So if you consider the point on the same surface, suppose if I consider the initial very next point on the same surface, dr also tending to 0, that means very next point but on the same surface, then this dr direction, the dot product with that is coming out to be 0. That means del phi and dr are perpendicular. Correct or not? Del phi and dr should be perpendicular to each other, where this dr is nothing but a vector on the surface itself, because the initial point and the changed point considered on the same surface. Hence d phi equal to 0. Hence the dot product of dr and d phi is coming out to be 0. So from this we can conclude that, so the del phi value is perpendicular to the dr. Dr is nothing but a vector drawn on the same surface. Hence del phi should be exactly perpendicular to this dr. So this is the del phi direction. Got it or not? Understood? Is this understood? Others, other than Anjali, anybody else? Any questions? Because this is one of the very important concepts while finding out the surface integrals. Yeah. Great. So this is great. Okay. So del phi is nothing but a vector which is perpendicular to the surface. So del phi always will be a normal vector to the surface. So therefore del applied on a scalar function normal vector results into a normal vector at the point of surface. Fine. So that means if you want to find out a normal vector to a surface, you can simply apply del on that. So the vector that results into a normal vector to the surface. If you want to find out a unit normal vector, to the surface, phi equal to constant del phi. So del phi is a vector mod of del phi. So this is the magnitude, this is the n cap. So this is the important concept we need to be understanding. Del phi by mod del phi is equal to n cap. You can note down this. And the other concept that is involved in this is, that is the directional derivative. So the directional derivative is nothing but given a direction, for the particular direction, what is the derivative value? So here this del phi is a vector, del phi is a derivative, del phi is a derivative in the normal direction, obviously. Now you wanted to find out the derivative value in a specific direction, which means if there is a surface like this, and on this particular surface, the function, let us say this surface is keep on expanding. Let us say this is another surface, new surface after a certain time t. So this is initially when t equal to 0, and this is at t plus delta t. So this is a new surface. On this new surface, if there is an expansion like this, then the normal direction, the expansion will be obviously maximum to the surface. So because this is the normal direction to the surface. Now I wanted to identify the change in this particular direction, that is in any random direction of, let us say, g. So this is, I wanted the expansion in the direction of g direction. How much it is going to be, the magnitude? That is nothing but the change in the function value in the direction of g is nothing but the directional derivative. So change in the functional value in a specific direction g is called as directional derivative. So for that, what you need to do, you have to identify in which direction you want it. So that is in g direction. So for that, find a unit vector in the direction of where we need the directional derivative. Directional derivative and then do a dot product. Do a dot product with del phi. So this is the directional derivative. That means del phi dot g cap is the directional derivative. Got it? Understood? Any questions? Yeah. So it's not to find a vector in that particular direction. The magnitude of the change, if you want to find it out, you will be doing the directional derivative. Got it? It's not a vector. The dot product will result into a scalar, right? So the magnitude of the functional change in a specific direction. Yeah. Note down a problem. Prove that del r power n, del r power n is equal to n into r power n minus 2 capital R, where r equal to xi plus yj plus zk. So that is the position vector of the point x comma y comma z. Now can you prove that r power n? So this small r is nothing but given or not. So the relation is r is equal to square root of x square plus y square plus z square. So this is the value of r, small r. Now based on this understanding, try to prove that del r power n is equal to n into r power n minus 2 times of capital R, where capital R is xi plus yj plus zk. Done? Okay, great. So let me prove this. See this, del r power n. So this is from this x square plus y square plus z square. So this is equal to 2x. It implies dou r by dou x is equal to x by r. Similarly, dou r by dou y is equal to y by r, and dou r by dou z is equal to z by r. Now here, if you apply del on this, del r power n is nothing but I dou by dou x plus j dou by dou y dou z getting multiplied with, so this is r power n. So if you apply on this, so I times of dou r power n by dou x plus j times of dou r power n by dou y plus k dou r power n by dou z. So here I times of n into r power n minus 1 into dou r by dou x plus j times of n into of n into r power n minus 1 into dou r by dou z. Now, if you take n r power n minus 1 out, then this is I times of dou r by dou x. You can replace with xi by r plus yj by r plus zk by r. So this is n into r power n minus 2. So xi plus yj plus zk. So this you can replace with n r power n minus 2 times of capital R. Got it? Done? So note down one more. If u is equal to x plus y plus z, if u is equal to x plus y plus z, v is equal to x square plus y square plus z square, and then w is equal to yz plus zx plus xy, yz plus zx plus xy. So these are the three different vectors. Then prove that grad A, grad u, grad v and grad w are coplanar. Grad u, grad v and grad w are coplanar. So grad u means gradient of u, which is nothing but del u, right? So what he said was del u, del v and del w are coplanar vectors. So this is what he asked us to prove. So to prove this, what you need to do is, if three vectors are coplanar, the determinant has to be vanished. That means del phi has to be vanished out. Got it? So this is dou phi, dou u by dou y, dou u by dou z, dou v by dou y, dou v by dou z, dou w by dou y, dou w by dou z. So this determinant should come out to be 0 to find whether these are coplanar or not. So for a coplanar set, this is going to be vanished out. Understood? Got it? So this you can do on your own. So do you have any questions on this concept, gradient? Any questions? Okay, so you can complete this. So in the next class, I'm going to deal with the divergence and the curl. Yeah. So yeah, thank you. Yeah, good night.